Hi there, welcome back to A Slice of Physics. We're now going to build on the learnings from the previous video to look at an example of resistance and current. First, we'll calculate the resistance of some wires given its properties. Then we'll determine the current that the wire would carry when it's connected across known batteries. And finally, we will understand how to work with changes in resistance when the physical properties of the wire are changed. So our question for today states that wire 1 is an 8-meter long piece of copper wire. So we know the length of the wire, and because it's copper, the resistivity of copper is also given to us as 1.7 times 10 to the negative 8 ohm meters. And it continues to say that the wire has a diameter of 1 millimeter. So we know the physical properties of the wire. The question asked is, what is its resistance? And then what current will it carry when connected across the ends of a 6-volt battery? Then there's a second question about wire 2, and we'll get to that after we solve this first question. So as always, it's good to draw a picture of what we're talking about, convert those word problems to a single picture. So here's my wire. Its length is given to me as 8 meters, and its diameter, thickness, is given to me d as 1.0 millimeter. Further, I know this is copper wire, that's specified, and the resistivity of copper is given as 1.7 times 10 to the negative 8 ohm meter. Okay, so that's all the properties that are given to me, and the question asked is, what is the resistance? Here are the equations that we're going to need for this question. And so let's start with the equation for resistance, which is rho times L divided by A. Rho is the resistivity, we know its value. L is the length of the wire, we know its value. A is the cross-sectional area of the wire, and we are not given that directly, but we are given the diameter of the wire. So now if we rotate this wire so that its end is facing us, we would see just the circle. I've enlarged it a little bit over here, and the diameter of this circle is given as 1 millimeter. So what would be the cross-sectional area, which is this guy over here? The shape of it, as you can see, is a circle. When we're given the diameter, that's the shape we're talking about. So we can calculate the cross-sectional area. Area of a circle is just pi times r squared, where r is the radius. And since I know the diameter, I know that the radius is 1/2 of that. So this is pi times 0.5 millimeter squared. Now this will give me the cross-sectional area in square millimeters. I want it in square meters because the resistivity is given in terms of ohm times meters. So it's good to convert this to SI units. So this really is pi times 0.5 times 10 to the negative 3 meters squared. And when you do this in your calculator, you will get cross-sectional area equals 7.85 times 10 to the negative 7 square meters. So that's a very small cross-sectional area in units of square meters because the diameter of the wire is only 1/1000th of a meter, so that makes sense. Now we can go about finding the resistance because we know all the variables in that equation. So R equals rho times L over A, which is simply 1.7 times 10 to the negative 8 ohm meter, times the length, 8.0 meters, divided by the cross-sectional area, which is 7.85 times 10 to the negative 7 square meters. And you'll notice that I kept 3 significant digits for area, even though all the inputs have 2 significant digits, because for intermediate values it's best to carry at least 1 extra significant digit. And this, according to your calculator, will turn out to be 1.73 times 10 to the negative 1 ohms, again to 3 significant digits, but since this is the final answer, we can round it to 2 significant digits and write it as 0.17 ohms, or 1.7 times 10 to the negative 1. So we've answered this question of what is the resistance. The next question was, if we take a battery that's a 6-volt battery and connect this wire across the ends of a 6-volt battery, what current it would carry. So the current would go from the positive end of the battery to the negative end, and it's asking us for what this current would be. We can do that pretty easily using Ohm's law. That's this equation over here, which says that current is delta V over R. Delta V is the potential difference across this wire, which is the potential difference of the battery, which is given to us as 6 volts. So this is 6.0 volts divided by 0.17 ohms, and that, to 2 significant digits, is 35 amps. That's a pretty large current because this wire has a pretty low resistance. So we've answered both the questions in this first part. Now let's take a look at the second part. The second part says that wire 2 is made of the identical material, same copper, but it is twice as long and twice as thick as wire 1. And then it's asking what is its resistivity and what is its resistance. So let me use the space over here to do this part. So I've got wire 2, and what's given to me is that it's the same material as wire 1. And you'll remember that resistivity is the property of the material. It does not depend on the length or the cross-section area or anything else. It only depends on what the material is. And in this case, as the material is identical as wire 1, row 2 will simply be equal to row 1, and that would be 1.7 times 10 to the negative 8 ohm meter, as was given to us. So we've already answered the first question over here. It was kind of like a trick question to make sure that you don't try to use any of these equations to see how resistivity would change, because if you understand that resistivity is a property of the material, you will immediately realize that that hasn't changed in this case. And for the last part, what is its resistance? It's asking us for what is R2, and now we need to worry about the other parameters, and it tells us that L2 is 2 times L1, and diameter or radius of the wire, lowercase r2, is 2 times lowercase r1. The radius of the second wire is twice the radius of the first wire. So we know how length changes, but we also need to know how the cross-sectional area changes. So area 2 would be pi times r2 squared. And r2 is simply 2 times r1, so this would be pi times 2r1, the whole thing squared. And that squares the 2 as well as the r1, so this gives me 4 times pi r1 squared. And since pi r1 squared is just a1, this is simply 4 times a1. So by doubling the radius, I have quadrupled the cross-sectional area. That's because the area of this circle has the squared relationship with the radius, so doubling the radius quadruples the area. Okay, so now I'm finally ready to calculate the resistance. So R2 would be rho 2 L2 over A2. And now I'm going to put this in terms of the first wire because I already know the resistance of the first wire. So if I figure out how many times this is of that, I can just go and use this value and do that. So rho 2 is the same as rho 1. We figured that out here. So I can write rho 2 as rho 1. L2 is 2 times L1, so I can write that as 2L1 divided by area 2 is 4 times area 1. We just figured that out, so I can write that like that. And so this simplifies to 2 rho 1 L1 over 4 A1, or 1/2 rho 1 L1 over A1, which is basically 1/2 R1. So by doubling both the length and the cross-sectional area of the wire, I cut the resistance in 1/2. So numerically, R2 is just 1/2 of R1, which is here, 1.73 times 10 to the negative 1. And that ends up being 8.66 or 8.7 down to 2 significant digits times 10 to the negative 2 ohms. Now I bet a lot of you are a little bit uncomfortable with the way I did this. You might be more comfortable with saying L2 is 2 times L1. I know what L1 is, so I can just go here and say this is 16 meters. and R2 is 2 times R1, so I can say that if this is 2 millimeters, and then I can follow the same process, calculate A2 in meters squared, and plug that into this equation for R and get its resistance. And if you did it that way, you would still get the same answer. The reason I did it this way is because in science, proportional reasoning of the sort we did here is very useful in solving many problems and cutting through a lot of detailed steps and getting to the answer quickly. And so this is a useful method that I'd like for you to get some comfort with. So I hope those examples gave you some comfort level in working with resistance and current and resistivity, and gave you some additional familiarity with this method of proportional reasoning that's often used in science. Thanks for watching.